Good morning. I hope you're able to see the screen.
Yes, ma'am.
Right. So this is chapter number 4. It's called the lattice vibration. Those of you who have attended classes will know what is lattice. Okay. And maybe for your sake, I'll tell you. Let's say we are talking about some metal. So if it's a crystalline material, what happens is equispaced will be the, and you have to imagine this in 3 dimension. You have to imagine this in 3 dimension. I'm just trying to give you a lattice. Okay. So what will be sitting at the lattice? At the lattice, you will have either an ion or you may have a group of ions. Okay. So basically, this will be ions. Okay. And what will happen to the free electrons? If I'm talking about a positive ion, then I'm talking about free electrons, electrons which are not localized or belong to this particular ion. Okay, they will be the electrons. So these will be the free electrons which may be floating around or moving. Okay, so this is what we mean by lattice. So these are the lattices. The ions are sitting at the lattice. It is heavy. Okay, and lattices cannot move around like electrons. The free electrons, which are not localized to the parent atom, can move around. Okay, so keep this in mind. Now, before this, I want to show you a picture here. I'm sure you people have seen this figure in SPM. In chemistry, also, you must have seen it. This is a picture of potential energy versus the interatomic separation. So, in this chapter, I will be using the word atom and ion. Okay, but when I say atom, also, I'm meaning the ion. You must remember that. So, how do you interpret this graph? If I have a lattice here, and let us say I have one here, and let us say we are talking of two ions which are oppositely charged. And this is the distance between them. At this distance, this is the interatomic distance. At this distance, what happens is there is no interaction between them. There is no force of attraction or repulsion between them. Therefore, the potential energy will be zero. Potential energy is zero. Now, to form a bond, what happens? Two such ions have to come closer to each other. So, what happens when they come closer to each other? Let's say they are here. This first one is here, and the second one is now here. So, now you see that the potential energy is negative. And negative potential energy or minimum potential energy means more stability. Then, let's think of bringing it here. When it is here, then the potential energy is more negative, so more stable. Finally, you find that at this position, when the second ion is here, the potential energy becomes a minimum. Potential energy becomes a minimum. And this interatomic separation, when the potential energy is minimum, is called the bond length. This is called the bond length R naught. So at this position, the potential energy of the system becomes a minimum or the system is most stable. Okay. Now, let us say that you are moving it further. Let's say you are bringing it here. Let's say you're bringing it here. So when you bring it here, what happens? When you bring it here, you're finding that the potential energy is still negative, but it is no longer a minimum. So that is not stable. And again, if you bring it still closer, you find that the potential energy now becomes positive. If you bring it here, the potential energy becomes still higher. Okay, most unnatural situation, most unstable. Okay, so this is in terms of potential energy. Now, the same thing, let us look at it in terms of force. Here, this force is talking of repulsive, okay, and the negative force is talking of attractive force. So if I'm talking about two oppositely charged ions at a great separation, what is the force? The force is zero. There is no interaction between them. Now bring them closer. When you bring them here, you find that the attractive force starts dominating. Attractive force starts dominating. And there is no repulsive force, okay, in this region. And at this region, bond length, at the bond length R naught, what happens is there is no force. Please remember the net force is equal to force attractive plus the force repulsive. Okay, so till you reach here, there is in this region, you're finding that the force is attractive. But once you reach here, the force becomes zero. So the net force at R naught is zero. Okay, this is an equilibrium position, equilibrium separation. Okay, now think of moving it closer. If the two ions are now closer than the bond length, now what will happen is, you must remember that we are talking of, let us say, even two atoms. If we are talking, the electron clouds will start repelling each other. They will start repelling. So what happens is the repulsive force becomes larger. The repulsive force becomes larger. So repulsive forces are always positive. This will be the repulsive force. If you try to get it closer, the repulsive force becomes really large. Okay, but at the equilibrium position, the repulsive force and the attractive force will balance, and that is where a bond is formed. So basically what we have done here is we have discussed the potential energy versus interatomic distance, then electrostatic force versus attractive interatomic distance. So for distances above the bond length, for distances r greater than bond length, which force will dominate? Which force is dominating?
Repulsive force.
Which one? Attractive force. It's attractive force that will dominate when r is greater than r naught. So I'm talking of this region. Here you see the force that you're seeing, the net force is negative. So it is the attractive force. And for r less than r naught, which force will be dominating? Should I call you by name?
Repulsive force.
Repulsive force. And what is happening at r equal to r naught? At r equal to r naught, look at this. What is the force? The force is zero. The force is, net force is zero. Okay, so this is something that you have to remember, because we are going to use some of these ideas in this particular chapter. This you would have studied in chapter number 2 of this book, but in SPM you have actually covered this entire thing. So a syllabus is not about repeating what you already have studied. That's the reason why I'm just discussing what is the bare minimum. Okay, so now we have used two terms. One, we have talked about the lattice, and the other is the electron. And we are now going to discuss the role of the ionic and electronic motions. Ionic means the ion sitting at the lattice position. I told you it's heavy. Electron, on the other hand, is light. Electron is actually able to move, but then the ions and the other electrons localized to that particular ion cannot move. So when we say ion, we are talking about a group of nucleons, okay, or what is inside the nucleus, plus the rest of the electrons confined to that particular atom. And the electrons which have come out, they are actually free electrons. Okay. And in this chapter, so we have to remember that there is a role played by ionic and electronic motions in deciding the properties of materials. A few minutes back, I said ions cannot move. I said ions cannot move. Yes, ions cannot move. The ions sitting at the lattices cannot move. They can only vibrate. They can vibrate about their mean position. If this is the mean position, okay, it can vibrate. It can move like this. It can move like this. They can only vibrate. They cannot move away from their fixed position. But on the other hand, electrons can move. Okay, so let us see which are the properties that are going to depend on the motion of electrons. The motion of the electrons and the electron lattice interaction. Electron lattice interaction means I showed you the ions are sitting at the lattices and I said the electrons are moving. You have studied in physics in the first semester that the second semester that these electrons, when they are moving, there is something called mean free path. Between two collisions with the lattice, they move in a straight line, and after a collision, they change direction. You've studied all this. Okay, so that's called the electron lattice interaction. So the motion of electrons and the electron lattice interactions, they will decide the electrical properties of materials. Whether the material is a conductor, what is the conductivity, what is the resistivity, these things, the electrical properties are decided by the motion of the electrons and the electron lattice interaction. In the case of dielectrics, for example, or insulators, for example, there are no such electrons which are moving. Okay, therefore, the electrical property is that it is non-conducting. Okay, so motion of electrons or the electrons predominantly will decide the electrical properties of material. Okay, but then there are some properties which are decided by the lattice vibrations. I told you lattice will vibrate. The ion sitting at the lattice will vibrate. So we won't say ion anymore. We'll say lattice vibration. When we say lattice vibration, we mean the ion sitting at the lattice. So which are the properties that are decided? Essentially, thermal properties and mechanical properties are decided by lattice vibration. Thermal properties and mechanical properties. Can you give some example of thermal properties? Anyone? Thermal property. You have to interact, otherwise how do I know what's happening?
Like temperature or like specific heat.
Specific heat, how good a conductor it is for heat, or thermal expansion. When I heat some material, it can expand.
Yeah,
In
how
some
much
cases, the
conductivity.
expansion is small. So these are all heat capacity, thermal expansion, heat conductivity. Maybe I can write that also here. Thermal conductivity. So these are all the main properties called thermal properties. So thermal properties are decided by the lattice motion, the lattice vibration. Similarly, mechanical properties. Can you give some example of mechanical properties? Any example?
Elasticity
Elastic
or
properties. Very good. Elastic properties, hardness of a material, all these things are mechanical properties. So please remember, when I'm talking of the ions sitting at the lattices, we are talking of bonds. I showed you R naught. Pujita, were you here when I was showing that graph? Okay, we talked about a bond length. So we're talking of
yes, ma'am. Yes, ma'am. I was here.
we're talking of bonds. Okay, so that means the strength of the material that is going to be decided by these lattices and the way they will move. Elastic properties are decided by these lattice vibrations. And please remember, the lattices will undergo small vibrations. What is the meaning of small vibrations? Let's say this is a lattice point, this is an ion sitting here. So what will happen is they will vibrate about a mean position, but the amplitude of vibration will be, if this is the bond length A, the distances between adjacent ions is A, then the distance through which it will vibrate will be R much less than A. That's why they are called small vibrations. Small amplitude vibrations only will be there. So in this chapter, we are going to develop a classical theory. We won't touch quantum here. We will develop a classical theory to describe these small vibrations and how these small vibrations in crystalline materials will decide the properties of material, especially thermal properties. Okay, and we will talk about these things in terms of what are called normal modes. Normal modes. These are called the modes of vibration. So how these normal modes, when I say normal modes, let us say there are n modes of vibration for a given system. They will be called normal when these n are unique and one cannot be written as a linear combination of the other. Does this remind you of mathematics? In mathematics, you may be talking of a differential equation. Then you talk about particular solutions. You will be talking of, let us say, 3 particular solutions for a differential equation. You call them particular solutions because one cannot be written as a linear combination of the other two. But you also talk about something called general solution. What is general solution? General solution is a linear combination of the particular solutions. Do you remember what I'm saying in from mathematics?
Yes, ma'am.
Right. Similarly, in case of small vibrations also, when the lattice vibrates, these vibrations can be written in terms of normal modes, and a general motion vibration, you are going to see that it is like an orchestra. These atoms will not just like that, no, independently they will not be doing. In Tamil that word is called tani avardhanam. Tani avardhanam means if somebody is sitting in an orchestra, okay, let's say somebody has a tabla, somebody is having the trumpet, somebody has a veena. Okay, now this entire thing has to be orchestrated, only then you hear a music. Instead of being orchestrated, instead, let us say the fellow who is playing the ghatam or the tabla is simply playing to his own his own way. Okay, that's not an orchestrated music. Then what you get is noise, it's not music. Similarly, you're going to see that these atoms or these lattices, they dance about their own position, and this dance, is actually related. The different atoms will be dancing in a way, they vibrate in a way that you are going to see a beautiful picture emerging. Those of you from school days, you must have done uh, some programs. You have formations, right? When you're dancing, you make some formations, so like that you're going to see that these atoms also, these lattices, when they are vibrating, they are an orchestrated vibration, they are not independent of each other. Okay, but then to learn them, what we will first do is, when the teacher is teaching you the dance, they don't straight away start off with the formations, they start with each individual, they teach you the individual motions, and then you move to the orchestrated motion. Similarly here also, we start a chunk. The first chunk is going to be the motion of the individual atoms. Then you say that, okay, there are n number of atoms, they are all vibrating like this. Then we talk about their interaction and then go to a larger picture. Is it clear? Okay. So now to understand these things, we have to employ what is called the ball and spring model of a harmonic crystal. What is this ball and spring model? Ball and spring model simply means that, okay, simply means that you're going to take these atoms or ions sitting at these lattice positions as hard sphere balls. You've seen this in SPM also. When you talked about lattice, when you talked about BCC, FCC, and all there, you treated each of these as hard spheres, and the shortest distance they are touching each other. These things you studied. Similarly, here also, you will be treating these lattices, you will treat these lattices as hard spheres, and there is a bond, that means there is an interaction between them. So the interaction between them can be described in terms of a spring. So two adjacent lattice points will behave like two hard spheres with a spring connecting them. So the spring is what is keeping them together. And why the spring? Why should you use a spring and not a rod to connect them? We use a spring because we have to explain the vibration. We have to explain this vibration. Okay. And when they are vibrating, this distance, let us say, normally if it is A, then this distance can either be larger than A or less than A because of the vibration. Okay, so this equilibrium inter-ionic separation, let's say it is A, okay, and it is A because the attractive and the repulsive forces are balanced. But then they will not be sitting like that. They will be, the lattice will be vibrating, lattice vibration. And you know that for any motion, you need energy. For any motion, you need energy. Where is this energy coming from? This energy comes from the thermal energy. If this solid is at some temperature T, T means you need not think of heating. No, even room temperature is an appreciable temperature. Even a temperature less than room temperature is an appreciable temperature. So associated with temperature, there is a thermal energy. So when there is energy, these fellows cannot sit in their position. So they start vibrating. Okay. So when they vibrate, what happens is, let us say that this tries to move like this. Okay, let's say it's trying to move like this. When it moves like this, you remember your mass spring system from physics. Immediately, there will be a restoring force. A restoring force. And what is the job of the restoring force? The job of the restoring force is try to bring it back to equilibrium. So these atoms or ions sitting at the lattices are in a state of vibration with two forces acting. The thermal energy is trying to make them move like this, and the repulsive the restoring force is trying to bring it back to equilibrium. Then, of course, because of thermal energy, what happens is, let's just take only one lattice point. So because of thermal energy, they want to dance around their position. So what happens is, when they go like this, restoring force is trying to bring it back like this. And it gets back also. But because of inertia, it overshoots and now starts moving in this direction. When it moves in this direction, the restoring force acts in the opposite direction and tries to bring it back. Okay, so this restoring force, the idea of restoring force, you can bring in only if you imagine two atoms or two ions, adjacent ions, as hard spheres connected by a spring. And it is this spring behavior that explains a lot of elastic properties of materials. Clear? Okay, so you are modeling a crystal as three-dimensional array of hard spheres. If I just talk about one dimension, then I'm going to place them like this and then springs like this. But if I'm talking of three dimension, what happens is I can just imagine like this a crystal, and then I'm talking of ions in all the three dimension and then springs in all three dimension. And you're making another assumption that these springs are massless. You don't want any inertia coming because of the spring. So you treat them as massless springs. Okay, so the balls and the springs are respectively representing the ions and the coupling bonds between the ions. And then you're talking of restoring force. When I talked of restoring force, you should immediately remember Hooke's law. I told you that the extension will be the the contraction or elongation of the bond X will be much less than A. So that means you are within your Hooke's law limit. Or you can use your Hooke's law and say that the restoring force will be equal to minus Kx. What is X? X is any elongation or contraction from the equilibrium position. So the restoring force or the spring force or the Hooke's law force is Fs is equal to minus Kx. And what is K? K is the spring constant. Okay. Now, when I am doing this, I also want you to remember what you have studied in physics. Okay. I hope you remember. I hope you can draw a graph for this. F is equal to F versus X. X positive is elongation and X negative is contraction. Okay, you can see that this is a straight line equation. Therefore, Fs versus K will be, and another thing, F is negative when X is positive. Okay, therefore, you will get a straight line graph like this. Do you remember this? Hooke's law graph?
Yes, ma'am.
Right. And along with this, in that particular chapter, you have also studied how the potential energy changed as a function of X. And you have seen that the expression for the potential energy is half kx square. Half kx square, or you found that this potential energy variation was in the form of a parabola. It was in the form of a parabola. It followed the half kx square behavior, and at equilibrium separation, between two atoms, you are finding that the potential energy is a minimum. And for any other distance closer or away from the interatomic distance, you are finding that the potential energy is positive. Positive means it is not stable. Okay, so now Let us see how we go about this chapter. Each ion moves in a parabolic shaped potential well. This sentence is very important. Each ion moves in the parabolic shaped potential well of the force fields of their neighboring ions. Let's say this is one ion, this is another ion, this is another ion. This guy is going to have his potential well, this fellow is going to have his potential, parabolic potential, and this guy is going to be trapped between these two. This guy at the center is trapped between the potential well of his nearest neighbors, and we are assuming that Hooke's law is obeyed and the motions are simple harmonic in nature. Okay, now I'll give you a picture of how the ionic motion is going to be within the parabolic shape potential well of the neighboring ions. So here is a picture. These things are not there in your book. Okay, so here is one ion. This is the second ion, and this fellow is your whole hero sitting between the two. Okay, so you can see that these potentials of both these will combine. The potential of the first, if I call this 2 and if I call this 3, the potential well of 1 and 2 combine and give you a potential looking like this. Or in other words, this 2 is trapped in a potential well. This ion 2 or lattice 2 is trapped between the potentials of 1 and 3, and what you get will look like a well of this form. So which means what happens is, unless it has energy to jump over this, okay, it cannot break loose. So its motion is going to be confined here only. Is this point clear, guys? And how do I know this is the shape? So for that, look at this graph. This is the graph for one of them. Do you remember the potential energy graph? This is the potential energy graph for one of them. This is the potential energy graph for the second atom. And the combination is this thick line. Okay. So when it is sitting here, the potential energy is going to be a minimum. And what happens when you move away? Let's say it is moving a distance. Let's say it is moving a distance delta A. What is A? A is this distance. A is this distance. Okay. Now, when instead of keeping it A, if it moves from the equilibrium position by delta A, then there is a change in potential energy. So the change in potential energy is going to be given by half F delta A square. Remember, U is equal to half kx square. Few minutes back we saw. Okay. So here we are going to write in terms of change in potential energy delta U because of a motion delta A. Because of a change delta A from equilibrium separation A. Instead of A, if the separation becomes A plus delta A or A minus delta A, then there is a change in potential energy. So what is that potential energy? The change in potential energy is half F delta A whole square. What is this F? I'm sure you are able to see that this F is the force constant K. I'm writing that K and all to remind you about what you have studied in your physics. Okay, F is the force constant or the spring constant of a two-body oscillator. So when we are doing this discussion, we are pretending as if this fellow is no longer there. Okay, so we are talking about these two guys. Okay, so if you are talking about these two guys, then the change in potential energy because of a displacement delta A from equilibrium position is going to be half F delta A whole square. Clear? I can wait till one of you answer. I don't want Pujita this time, somebody else answer.
Yes, ma'am.
Okay. I'm deliberately going slow so that it becomes easy for you to understand. Okay, now. I said orchestrated motion. So I have given you an example of a one dimensional material don't exist. Okay, but then we are doing modeling. In physics, it's always model. So when we are discussing models, we talk about a simple thing and then extend that idea to a more complex situation. So that's what we are going to do here. So there are two types of movement from equilibrium that can happen. One is called longitudinal and the other is transverse. So look at this. For example, you can see that this, 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 these are all the equilibrium positions and the separation is A. Separation is A. But then if there is a disturbance, now look at this. You can see that this disturbance, this is not getting disturbed. This got disturbed by a small distance, small green arrow. This gets disturbed by a larger arrow. This gets disturbed by a more larger. This smaller. This is still smaller. Here, nothing. So are you able to see that orchestra that I was talking about? So displacement from equilibrium, each cannot behave as if nobody else is existing around it. They are all connected. They are all connected. So what happens is movement of one gets reflected in the next one. So these movements will be, and look at this here, the displacements are, you can see the disturbance. The disturbance is traveling. You can see the direction of disturbance. You can see that the disturbance is traveling in this direction and the movement of the ion from equilibrium position is along the direction of the disturbance. Is along the direction of the disturbance. It's called longitudinal. Okay. Now transverse. What is transverse? In transverse, you see here, these are that orange line. On the orange line, they should all be sitting. That is equilibrium. But then you're seeing that the displacements are away and perpendicular. They are away and perpendicular. Some of them are moving along the positive, some are moving along the negative, but perpendicular from the equilibrium. So this is a transverse. Okay, and here I've shown you a two-dimensional representation of this orchestra. You can see here that the shaded dots are all the equilibrium positions, and you can see the motion. Can you see that there is some kind of a pattern in the motion of each of these lattice points from their equilibrium position? You find a certain pattern. That's what I called as the orchestrated motion. Similarly here, it is transverse. It goes like this. You can see. It's transverse. But the motion from equilibrium position is, there is a pattern. There is a certain pattern. Okay. Whereas in this case, what's happening? You're seeing that it is in this direction. This is longitudinal and this is transverse. I hope you understood the word transverse and longitudinal. If the direction of the displacement from equilibrium is along the direction of motion of the disturbance, then it is called longitudinal. If it is perpendicular, it is called transverse. You can see that the disturbance is traveling like this only. So what will happen is, it's like this. Like this, like this, like this, it goes. Okay. So now, how do you know that this ball spring model exists? We talked about some ball spring model. So in support of ball spring model, I'm going to give you 3 points. You know elastic modulus of elasticity. Can someone give me the equation for modulus of elasticity? Elastic modulus, Young's modulus. Stress by strain, you remember? Stress is force per unit area. Strain is change in length by original length. You remember this? School level, yeah? In intermediate, school level, yes. So this is elastic modulus. So let us actually calculate using this ball spring model. If you calculate the elastic modulus using some software, you will get it around 10 to the power of 11 Newton per meter square. Okay, you do this modeling and then make a calculation. So it comes to be around 10 to the power of 11 Newton per meter square, which is the order of Young's modulus of metallic springs. Okay, so this elastic modulus calculated, modeled and then uh, estimated is of the same order of the Young's modulus of springs, metallic springs. So that means we are not really off the mark. And how are we making this calculation? We are making this calculation because we know how you theoretically calculate, I'll tell you. You know, in a given block of material, how many atoms are there. You know how many atoms are there, and you know what is the interatomic distances. So let us say you are applying a stress, you know what is the change in dimension, so you know how much the atoms came closer. Okay, so like this, you can actually do a modeling and calculate. So when you calculate, the modulus of velocity is coming out to be 10 to the power of 11, a realistic value. That's the first point. Next thing, from the modulus of elasticity, we're not getting into the equation. You can get the frequency of oscillation, because after all, it's oscillating about the main position. You calculate the frequency of oscillation, and it is found that it is in the infrared region. You know the electromagnetic spectra, there is something called the infrared region. You're finding that the frequency of oscillation is in the infrared region. And we know for a fact that this is the vibrational frequency of solids. How do I know that this is the vibrational frequency of solids? In chemistry, you must have studied a bit of spectroscopy. You must have studied that when you allow electromagnetic radiations of certain frequency to fall on your material, depending on what is the vibrational frequency of the atoms there, it will absorb the radiation. So whichever frequency gets absorbed, that is the vibrational frequency of the atoms of that material. And it is found that, okay, the calculation that we are doing matches with the normally seen vibrational frequency of solid. So that means theory and experimental observations are matching. Then third thing is, when do you use ultrasonic sound waves will have large lambda. Sound waves will have large lambda much greater than A. When you are passing this large lambda, your sound wave should not be seeing these lattice points. Instead, it will see this entire block of material as a continuous medium. It will see it as a continuous medium. And it will move through the medium, and there is a velocity of propagation. The theoretical equation for this is under root of E by rho. That is the velocity. So if you do a calculation using this E and the rho of the material, you're finding that it is matching with the experimental values of ultrasonic velocities. You can actually do the experiment. You take a material, you allow ultrasound waves to pass through. Okay, the velocity that you are getting is matching with the calculated velocity. So that means our model of ball spring is okay. So this is fine. So we can just use this and go ahead and study materials. So as a first step, what we'll do is we will take a simple model. The simple model is going to be one dimension. You're going to assume that the material is made up of a line of atoms sitting at the lattices, okay, and then there is spring connecting them. Or you're talking of a linear chain of n identical atoms. And then we are going to see their vibrations, and then we are going to arrive at some equations. So did you understand this chapter till this point?
Yes, ma'am.
Yeah, okay, if you have understood. So what we will do is I am deliberately going slow so that you understand every line that we are talking here. The first two chapters, guys, you did not come to class. This is not at all what I would expect from you. Please come to class. If you don't do well in the examination, it's your future. Okay, so I think I'll just stop the session here. And I'll stop the recording also.